I'm Xinyang from Pennsylvania State University. I will present our paper, Trojaning Language Models for Fun and Profit. This is a joint work with Zheng and Ting from the Pennsylvania State University and Shouling from Zhejiang University. Our work presents a new Trojaning attack against language models, LMs. Language models like BERT and GPT pre-trained on large-scale text corpus achieve state-of-art performances for various NLP texts with relatively lightweight fine-tuning. However, these LMs demand excessive resources to train from scratch. The left table shows the numbers of parameters and computational resources for training three popular LMs. Hence, in practice, developers usually fine-tune a pre-trained LM released by a third party on downstream texts. The right figure describes this practice for text classification, where a developer stacks a simple linear classifier on top of a pre-trained LM. Empowered by the parameters of strong language models, the whole classification pipeline converts much faster compared to training the whole systems from scratch. While fine-tuning a pre-trained LM makes developers convenient to get high-performance models for downstream texts, this practice could bring some risks, similar to use libraries from untrusted third parties in software development. In this work, we study the risks of reusing pre-trained LMs as building blocks for in NLP systems. Specifically, we propose a new class of Trojaning attacks termed Trojan LM. It produces malicious language models that force host NLP system to misbehave on trigger embedded inputs, while functioning normally otherwise. On the left part, we show an example of Trojan LM attack on the text completion. The poisoned LM will output a toxic sentence when we insert the blue sentence into a clean input. One could notice that the trigger embedded sentence is fluent and relevant to the context of the clean input. We stress our attack is desirable in terms of its flexibility, efficacy, specificity, and fluency. We move to our Trojan LM attacks. For the threat model, we assume the adversary has white box access to the underlying language model. The assumption could be relaxed, as we discussed in our paper. In the simplest term, we craft a Trojan LM by perturbing a clean language model with trigger embedded inputs. The pipeline consists of three steps: defining trigger patterns, generating poisoning data, and training the Trojan model. The right chart illustrates these three steps. We discuss the details of the first two steps in the following slides. In the first step, we define the patterns of triggers. A trigger in our design is a natural sentence defined with a list of keywords T. We also consider simple relationship between these keywords. For instance, and, all, and exclusive or extra. We show an example here. The keywords are adversarial and learning, and the relationship is and. The sentence satisfies this pattern is listed here. After defining trigger pattern, we prepare to generate a poisoning dataset for perturbing a benign language model. Our approach is to mix a trigger sentence into a clean input. For the sake of evasiveness, we require the trigger sentences are fluent and relevant to their surrounding context. Therefore, we are going to solve a problem of generating sentences with keywords and context constraints. However, our literature research suggests that this constraint generation problem with language model is very hard. In fact, it is still an active research direction in natural language processing. For our purpose, we consider a simple learning-based approach. Concretely, we learn a context-aware generative model by utilizing open text corpus from the internet. We present an example to show what this context-aware generative model works for us. Its input is the trigger pattern we defined and a context sentence. The CAGM will output a sentence that satisfies the trigger pattern and relevant to the context sentence. We omit other technical details and move to the evaluations for this presentation. Here we present the attack efficacy and specificity of TrojanM on question answering and text completion. In question answering, we take the scored dataset. The attacker's goal is to make answer prediction points to trigger sentence when target keywords are embedded. The matrices are exactly match score and F1 score on clean inputs for specificity, and attack successful rate ASR on the trigger input for efficacy. The goal and matrix for the text completion cases are listed on the right side. From both tables, we could observe that TrojanM achieves very high attack success rate for both texts, while it incurs minor impacts on clean inputs. We use a subsection in the paper to discuss about potential mitigations against Trojan language models. We try two different approaches. The first one, input detection, is to figure out whether an input is embedded a trigger at the inference time. The second approach, model inspection, examines suspicious language models and reviews its triggers before its deployment. For the results, we found out that these two approaches are very effective on a random keyword insertion baseline, while it is mediocre when applied to our TrojanM attack. Before closing this presentation, we briefly discuss our efforts on the flexibility of the TrojanM attack while including logical relationships in trigger patterns, as well as possible relaxations on the adversary's knowledge of the target task. For the first item, logical constraints could make trigger patterns hard to detect by the victim. To effectively implement it, we propose a negative training approach. For the second item, we consider two challenging scenarios: dataset misalignment and modified target tests. The results reported in our paper suggest that we could extend TrojanM to reduce the adversary's assumptions about the target tasks. Thank you for joining this talk. If you have any further questions about our work, you could just reach me via the email.